Okay, well, thank you, Harry, for the kind words. It's almost frightening to start a talk after that introduction, but I hope I'll be able to live up to some of your expectations. Harry specifically asked me to talk about at least partly of these historical things. And so I chose this extremely unsexy name, Neural Networks and Machine Learning Research at the Laboratory of Computer Information Science, Helsinki University of Technology. I try not to bore you to death. I will kind of cover something like 40 years of time of my own research, other research of that laboratory, but also at the same time I have to touch on the research worldwide, what happened in this field since 70s. And I start with the prehistory, which here means at times when almost none of you were born, which is 1965. So, okay. This lab was established by Teuvo Kohonen in 1965. He got a professorship at the Department of Technical Physics at Helsinki University of Technology. And his duty was to establish a lab for electronics and mostly, at that time already, it was mostly digital electronics, not analog electronics anymore. This lab has changed names many times. Teuvo chaired it until he resigned from his chair because he became a permanent academic professor, and then I got his chair and then chaired it until 2009 when Aalto University was established and there was restructuring and these labs were merged. And now it's a part of this big computer science department at Aalto. Now, of course, very much we're talking about neural networks. Teuvo started his research into neural networks already in early 1970s. What he worked on was so-called associative memories, and then also subspace classifier speech recognition. He's a good engineer. He has theories on the neural system, but he always wants to put those theories into practice by devising some practical algorithms for some real-world tasks. And of course, his big achievement was the self-organizing map, which he invented in early 80s. But he's going to come here and tell about his own achievements, so I'm not going to talk about that at all. As Harry said, I completed my PhD in 1977 with Teuvo. Part of actually the topic of my thesis was how to build associative memories in neural networks, recurrent networks of neuron-like elements. This has quite an overlap with something that John Hupfield did 5 years later in early 80s. And we actually had some non-friendly correspondence with him at the time. But of course, these ideas, it's my PhD thesis, but really the ideas largely came from Teuvo because he was working just on these associative memories. And then, as Harry again said, I went to postdoc at Brown with Lian Cooper. And the title of this paper shows what neural networks meant in the 70s. So it was very much, actually it was called neural modeling. And what we really tried to do was to look at the experimental facts that were found from especially the visual sensory circuits of animals like cats or monkeys, and try to model what are the mathematical rules that govern these activities. That was one side of neural networks. The other side was definitely putting things into practice. And during my postdoc period, I wrote a book on subspace methods of pattern recognition, which is a kind of a classifier inspired by some neural theories, translated into Japanese and Chinese. This was fun, and it was nice to do neural networks in this small group of people. We were very, very small group. The good thing is that we kind of met each other and we knew each other. So guys like Terry Sejnowski, Geoff Hinton, Mike Jordan, we kind of met regularly and we really knew each other, people of about the same age. And it was very fun, but then what happened in early 80s was that we suddenly met face to face with the mighty opponent, which was artificial intelligence, AI. And definitely, let me say, AI did not mean neural networks in 80s. It was something totally different. The roots of AI were somewhere else. True AI was symbolic, definitely symbolic. It was search, logic, frames, semantic nets, languages like Lisp, Prolog, and especially in early 80s, what became very hot were the so-called expert systems, or knowledge-based systems in which we have facts and rules and then you infer things. That was a big thing. And it was really, for instance, MIT professor Marvin Minsky, I remember well his talks. He was quite antagonistic to at least certain kinds of neural networks. And we had problems in convincing people that there is something in this. Actually, the practical results were not so great with the computers that we had at that time and with the algorithms that we had at that time. But then in late 1980s, what happened was that slowly these neural networks and also probabilistic, especially Bayesian reasoning, kind of sneaked into AI, and the antagonism within AI people started to become a little bit less. One really important thing was this Le Net that Yann LeCun introduced in 1989, which is a multi-layer, now we would call it a deep convolutive neural net, deep CNN. It has some convolutive layers here that combine activities and then feed them into the upper layers, and finally a classification layer. This is for classifying handwritten numbers. And this was trained by backpropagation. This was really influential, and as you see now it's how much? 28 years, and now this is still going strong. Teuvo became very famous in the 80s. I started to get citations in the 80s, and for instance, Teuvo was already general chair of some big international neural network conferences like in San Diego and Washington. But then we decided that, okay, Europe first, and we decided to establish a European conference called the International Conference on Artificial Neural Networks, ICANN. The very first one was in Espoo with Teuvo as the chair. Actually, the 25th anniversary was just last September in Barcelona. And I had introduced this Oja rule, as Harry said, in early 80s. Started to get citations, but now I had to move on, and I started to wonder how to make PCA nonlinear, how to get nonlinear principal component analysis, some kind of nonlinear function from high dimensional space into lower dimensional space that would reveal some components that would be as useful as principal components. And what I suggested in this conference was in this paper, Data Compression, Feature Extraction, and Auto-Association in Feed-Forward Neural Networks. And this is exactly taken from that paper. So nowadays you would call it a deep autoencoder. I did not use those words, but it is the same. So the idea here is that this is unsupervised multi-layer network. So you just you put your X vector here as the input, but also the same vector as the desired output. And then here is a kind of bottleneck layer that has much smaller dimensionality, and something valuable happens in the bottleneck layer when you train this with backpropagation, and then you can use this for dimensionality reduction, kind of just removing this end, and then you just feed in anything here, and then you get the low dimensional representation out of this layer. This was really one of the very first papers on multi-layer deep autoencoders, which are quite popular today. It was difficult to train, and I completely dropped research on this. Maybe I should not have, but I did. And so other people went on. There was some result by Hinton, Bengio, and many others. Okay, that was the prehistory. And now for the past 25 years, which I consider kind of history. First about what happened in the lab, then something about what happened in my own research. We have been very lucky to be able to expand and get very good finances, mostly because Academy of Finland has given us 4 consequent so-called centers of excellence. Those of you who don't know, the kind of government financing system in Finland. These are rather big grants, like 1 million euro a year. That's the order of magnitude, which can be used for hiring many postdocs, for instance, and buying equipment and so on. It's kind of free money. Very nice. The first one, the Neural Networks Research Center, was still Teuvo's time, but then this continuation we already did together, because in those days retirement age was 65, and Teuvo was born in 1934, so you can count that exactly then he had to retire, and he left everything to me. Erkki, you take care of things. So we had this continuation, but then I managed to get myself this Adaptive Informatics Research Center, and then the Computational Inference Research Center that is incidentally ending this year. And what went on in this center? So the lab that was originally very small, Teuvo had just a few students, and that's it. It grew into a lab of like more than 100 people. In this Adaptive Informatics Research Center, that was about 10 years ago. We had several groups. If I give you the names, so the algorithms and methods was led by Professor Juha Karhunen, who is at Aalto University. Then the multimodal interfaces was led by Mikko Kurimo, who is now professor at Aalto. Speech recognition at electrical engineering. Bioinformatics and neuroinformatics was led by Samuel Kaski, who is now academic professor at Aalto. Computational cognitive systems were led by Timo Honkela, who is now professor at the University of Helsinki. And adaptive informatics applications were led by Olli Simula, who retired, and Momolen Das, who is now professor in Iowa. So lots of these people kind of became professors, and they had students and students. I don't know if there may be some people here actually who got their PhD from the lab still when we had this AIRC. Then we went on to COIN, Center of Excellence in Computational Inference, and here we had a slightly different structure. We had three kind of topics. One was still this data analysis, machine learning. That is kind of my topic, and also Sami Kaski's topic. But then we had the computational statistics and computational biology, led by Jukka Korander, who is now a professor in Oslo, and Erik Aurel, who is a professor at KTH in Stockholm. And then a real addition was this computational logic, intelligent systems with Ilkka Niemelä's group. Ilkka is the provost of Aalto University, but his hobby is kind of computational logic, different kinds of logics. And this was a real effort now to bring together machine learning and what I would call traditional AI, inference using Prolog-like inference methods. And Petri Myllymäki, of course, you know, I think he's director of HEAT, I believe, today. And of course, there were lots of connections. What did we do in these centers of excellence? Of course, during this kind of short talk, it's impossible to go into any detail, but this is one picture that shows some of the main topics. So the big ellipses are kind of central topics, and then the smaller ones had a bit smaller groups. We still had these self-organizing maps and ICA, which is independent component analysis, as very important topics. And then visualization, nonlinear dimensionality reduction was a big thing. That's also unsupervised learning. These both are unsupervised learning. And then probabilistic latent variable models, Bayesian models, of course, can be supervised and unsupervised. And then many other things, linear mixtures, nonlinear blind source separations, sparse PCA, even relational models again here, and things like that. Now, this ICA is a nice story by itself. How many of you know what ICA means? Not everybody, so even if I wrote a book. Okay, I'll just show what ICA means. So let's have just a demonstration. Imagine that you have these 9 images that are independent in the sense that, for instance, if you if you see 8 of these images, you cannot predict what is the 9th image. There's no information between the images. They are kind of independent. Now imagine that that these would be mixed into this kind of mixtures, and the mixing happens so that you multiply each image with a number. In our case, a random number. But for instance, the first image you multiply by 0.2, minus 0.3, 0.8, minus 0.650, something like that. And then after multiplying, of course, when you multiply with a negative, then the picture becomes negative. Black becomes white and white becomes black, and so on and so on. And then you add them up, just pixel by pixel. And then you have this first mixed image here. And now you take another set of 9 numbers, another mixture, and then you had the second one, and so on and so on. This happens, for instance, in the so-called cocktail party problem, when lots of people are speaking in a room, and depending on where you are standing, these sound waves come into your ear with different strengths depending on the distance. And now the problem in ICA is simply to have only this data, nothing else, and then this assumption of independence. And then you have an algorithm, and then you get the independent components of these 9 images, which are these. I don't know if the resolution is enough, but if you look closely, at least in the front row, you can see that actually the girl's face is not exactly the same as the original girl's face. There is some mixture still of this not image and the girl's face, and here you can see the waterfall and the flower. They have some mixture, but these are the independent components. The actual first images were not truly independent. There has some correlations, and that's the reason for that this is not exact. But you can understand that showing this kind of demos convinced many people that there must be something here in this technique. And we wrote a book that has been cited very well, something like over 9,000 times in Google Scholar. Aapo Hyvärinen was my postdoc, and now he's professor in London. Juha Karhunen is still in Aalto. Okay, and then I'll go to my own present research topic, which is matrix factorization for data analysis. In a way, also this PCA thing and ICA are matrix factorization, so they also fall to the same category. And now this is more like a scientific presentation that I'm starting to give now. So remember this picture, and now this falls perhaps here: sparse PCA, non-negative projections, DSS things like that. That's what I'm talking about now. Can you see anything? This is not the best audience room that I've seen, so at least some of you perhaps can see something. But the idea here is that you have a data matrix X. That is very common in doing any kind of data analysis. You start with the data matrix that contains all your data, depending on the application, of course. And now you want to decompose this matrix into a product of 2 other matrices, W and H. Of course, this would be completely trivial if we had no constraints. Then simply W would be the identity matrix, and H would be X, and that's it, then an exact representation. But that is not allowed because the dimensions are such that is W and H have a lower dimensions than X, and so you cannot just put in an identity matrix. So we have a situation like this. A typical example where this works really nicely is a spatio-temporal data. Imagine that your data matrix has some spatial measurements, parallel measurements of something taken at the same time. And then time moves on, let's say 1 day, 1 second, and then again you have the same measurements. So this kind of measurement vector is proceeding from time point to a time point. And now we have this space-time matrix. And now if you do this matrix factorization into a low row dimensional W and low column dimensional H, then it turns out that this is a kind of spatial matrix explaining what is the spatial thing happening in this matrix, and this is the temporal matrix. If you remember your matrix algebra, I'm not going to show any equations, but if you remember your matrix algebra, then this kind of matrix product, WH, can be represented as, take the first column of W and the first row of H and multiply them together. Then you have what is called elementary matrix. It still has the full size, but the rank is only 1. Then take the second column and the second row and make the same matrix and add it to the previous one. And so it's a sum of these column row matrices, and that is this WH product. And now we can imagine that each of these individual column row things is a kind of component, where you have in the vertical direction you have the spatial component, and in the horizontal direction you have the temporal component, showing how this vertical component is evolving over time. And this is an example, global temperature over the Earth in January 2000. You see how the day is changing. This was done with Harri Valpola, incidentally, and Alexander Ilin. They are both here. You see how time is changing here. Now, this is not the data matrix, but imagine that you would scan this matrix row by row, and you would have 10,512 points. That would be one column, one spatial column here. And then if we are talking about January 2000, then we would have 31 such columns, one for every day, and that would be the data matrix for January. But now we have much more measurements, actually for 20,440 days. So we have this kind of data matrix. And now, using a method called DSS, I have no time really, no chance to explain that. One of these components that we got out, remember it had this spatial component and the temporal component. If the temporal component looks like this, which means obviously some kind of global warming because it's going up and up, then the spatial component looks like this. So our bold prediction was that, okay, in global warming you should go to Australia and see whether it's actually cooling there. If it is, then our model is perfect. But okay, we have to remember that this is unsupervised data analysis, exploratory data analysis. We had no, well, there was some little bit of knowledge about how these variations in temperature work, but very little. So this is basically a blind method. And so of course now we have to go to the Institute of Meteorology and talk with them, and we did, but they were not very excited. Actually, climate is, of course, is one of those things in which there's nothing independent. So anything related to independent component analysis is doomed to fail in climate studies. But this is not ICA, this is much more advanced, but still. This goes to show what I mean by this matrix factorization, so just an example. So there are lots of applications for this, the contents of this data matrix X. They could be signals, time series, spectra, phase images, DNA microarray, user ratings of movies, document term histograms, very much used in text analysis, and so on and so on and so on. And using this kind of matrix factorization reveals something deep about those phenomena. For instance, in this Netflix competition, there were about 480,000 users that had rated about 17,000 movies, but the rating matrix was very sparse. Of course, there's nobody who can really look at 17, well, teenagers of today, maybe they can look at 17,000 movies on Netflix, or they would not watch it on Netflix. But nobody really can, so it's a very sparse matrix. And one of the methods that won the competition, or the method that won the competition, one of the kind of sub-algorithms was based on matrix factorization. It's a kind of collaborative filtering problem. Actually, even in our lab, some people tried this. I was not involved in that, but this is again one example of this kind of data matrix that has two dimensions, in this case films and users, and then the result you can use to predict how a certain user will rate a certain movie that he has not yet seen. And so it can be used for recommender systems. Now, that already was an example of non-negative matrix factorization, which is a very powerful method, actually simple but powerful. It means that this data matrix is totally non-negative, meaning that each element is only allowed to be 0 or a positive number. And the same holds for W and H. And now we must have, of course, some criteria. Typical would be like maybe even the least square error between X and WH, or rather some kind of divergence depending a little bit on the problem. This is called non-negative matrix factorization, and there's a large literature on that, even textbooks. It's today quite, I mean, when I speak, it's an active research topic. For instance, in tensor factorizations, like a vector is a one-dimensional array, and a matrix is a two-dimensional array. A tensor is like a three-dimensional or four-dimensional, whatever dimensional array. And obviously, you can kind of expand this matrix factorization into tensors, so you just have lots of multiplicative factors that reveal something about the tensor contents. In mathematics, numerical mathematics, this is called low-rank approximation. They are very interested in these techniques. Missing data can be handled with this. This obviously relates to robust PCA, sparse PCA. And then an interesting approach is symmetric NMF and clustering. And with my postdoc Zirong Yang also here, actually he got me interested in this problem. So clustering is a very classical problem, and the way to represent I assume you all know what clustering means. So you just have a set of data, and you kind of, in an unsupervised way, you divide it into certain groups, and these groups are called clusters. It's one of the most typical data analysis methods that you can have. It's a very classical thing. And the way to show kind of mathematically or even in a computer program the clustering result is to use this kind of matrix. It's a cluster indicator matrix. For instance, in this case, I have 10 vectors or any items. They don't have to be vectors. And 10 any items, and then I have 3 clusters. And this kind of matrix means I can read from this matrix that this first vector is in cluster 1. The second vector is in the third cluster. The next vector is in the second cluster. You see what I mean? One indicates which cluster. And you see that all the rows must have only one non-negative element, because an item cannot belong to several clusters, so that's very clear. And one of the most classical methods, K-means clustering, that goes like this. You have this, imagine that these points are two-dimensional points like this, and then you start, and imagine that you want 2 clusters. You just start from some arbitrary points here, and then each of those points chooses which of points A or B is closer. And these arrows show that, for instance, for this one, B is closer. For that one, A is closer. And now what happens is that these A and B are pulled into the centers of those data clouds, which they selected, like that. This is K-means. What does this have to do with the non-negative matrix factorization? Very much, actually, because this K-means algorithm, it can be shown that it's minimizing a certain cost function. Those of you who know clustering, you know this cost function. Those of you who don't, it takes too much time to explain it. But there are these cluster centroids, and then these points, and this is kind of measuring how close each point is from its cluster centroid. Must be as close as possible. But putting this into matrix vector form, we get this kind of criterion. Again, those of you who know principal component analysis recognize this as the PCA criterion, but with an important difference. In PCA, this H would be a kind of any matrix. It has no constraints, and here it must be binary. So this is a combinatorial optimization problem, binary PCA in a sense. And again, if you know your PCA, then you know that minimizing this kind of norm is same as maximizing the trace of this matrix X transpose X, H transpose, which allows us now to use the kernel trick, because anywhere when we have an algorithm that only has this data matrix in this kind of form, the X only appears as X transpose X anywhere, then you can always plug in the kernel instead of XTX, and then you can hugely enlarge this to kind of nonlinear processing. I mean, the Zirong, we had a paper on this. And finally, the latest result is a novel clustering method, DCD. First, I will define another matrix, please don't get bored, called cluster incidence matrix, which is a binary matrix. Let's say if you have 10 items again that you want to cluster, it is a 10 by 10 matrix, binary matrix. If there's a 0 in a certain element, then it means that this item and this item are not in the same cluster. If there's a 1 in a certain element, it means that this item and this item are in the same cluster. Remember, it's indexed by the items, both row and column. So it's a 10 by 10 matrix in the case of 10 items. So this is very simple. And now there's a nice similarity measure that we used. Let's assume that we have some. Let's assume that we have a similarity measure for these items. The items don't have to be vectors. They can be whatever, animals or documents, whatever. But assume that you can define a similarity between them, so that if two items are, let's say, completely similar, then the similarity is 1. If they are completely dissimilar, then the similarity is 0, and then everything between. And now isn't it very natural to say that the difference between S and M should be as small as possible, because if two items are very similar, then that element in S is almost equal to 1. And they should go to the same cluster, of course, because the whole idea in clustering is that similar things go together and different things go to different places. And so in M, we would have 1 there. If two items are completely dissimilar, we have 0 in S, and also we should have 0 in M. So it's a kind of natural criterion. The problem is that M is not a continuous valued matrix. It's a binary, basically a binary matrix. It is a binary matrix with some constraints. There are some technical constraints like the row sums and column sums of M is symmetric, so the row and column sums must be made equal to 1, and actually this similarity must be somehow also normalized in a suitable way. But then it's still a combinatorial problem, and what we did was to solve it with a clever relaxation, and that is so-called data cluster data random walk. So you can imagine that we have probabilities of this data entering a cluster and then going from one of the data items to a cluster, and then from cluster to a data item. And now these probabilities must be fit into this criterion, so that if, let's say, this jth data element and ith data element are very similar, then there should be a large probability that through some cluster they can kind of jump to the cluster and then jump back. But what cluster, that depends on then, of course, on the similarities of the other items. Anyway, this can be solved, and we published a paper with Zirong and Jukka Korander in a Journal of Machine Learning Research in last year. I would not be talking about this if the results were not so good. I mean, look at this. These clustering results. This is our DCD, and these clustering. These all are problems in which you know the ground truth. And so this number shows the same as a supervised classifier would show. For instance, 0.87 means that in this phoneme class that kind of classification error is 13%, and the correctness is 87%. But remember, this is clustering. This is not supervised classification. And what is quite impressive is, for instance, this MNIST result. You know, MNIST was the handwritten number database. MNIST result is 0.97. And I just challenge you to take any supervised classifier software, and try to get 0.97 accuracy with that. You can sooner or later you can do it. I think the best result is now with deep learning. The error rate is only by 0.23, so it's 99.77. But it is supervised. It is trained with 60,000 characters whose class we know. and then tested with 10,000. Here the whole group is just used for clustering. No class information is used. This seems to be a very efficient method. Okay, then my time is up and I'm coming to the end. So, and now I come back to the actual topic of my talk, that was what happens in the so-called KISS lab or Info lab, the old computer information science laboratory. So now it's part of this Aalto School of Science, and it's much less isolated, and there are much partnerships with the other groups, HEAT, Helsinki University, and so on and so on. I did not mention at all any company relations that of course we had lots of projects with the big and small companies, but I really only here talked about research and a little bit of, well, not even teaching now, but I would say that we have had a strong impact on machine learning in Finland and in the world, if only for the reason that so many talented PhDs have gone out of the lab and established the startups in Finland and moved around the world. But also in teaching, that the final note I want to give is our Master of Science program. This is not an advertisement because you probably have a Master of Science, but we have a Master of Science program called Macadamia, Machine Learning and Data Mining. I think it's the first data science master program in Finland. We established it with Heikki Mannila, who is now the president of Academy of Finland, in 2008, I think. I tried to find out when it was, about 10 years ago. And right now, this spring, when you look at Aalto School, the 4 Aalto Schools of Science, then it turned out to be the 3rd most popular Master of Science program when you measure it by the number of initial applications that we got. This is amazing because before it's only the whole mechanical engineering. You know what is mechanical engineering? It's building anything from ships to cars and everything, or architecture, which is rather a big field in Finland. And now this tiny, narrow field, machine learning and data mining in computer science, is number 3. Below that we have industrial engineering, building technology, everything. So this means that this field is hot. Somehow we have managed to do something right, because so many foreign, and now we even have these tuition fees, so that doesn't seem to hurt. So many Finnish and foreign young people have kind of been attracted to this lab to learn about these things. So I wanted to end with an optimistic note, and that's what I do. Thank you for your attention. Thank you.
So I'm quite new to the topic. What does it mean that you're researching algorithms? Do you test which is better, and what can you guess from research that this algorithm works better on this, or what does it mean?
Okay, typically the way to test it is just some kind of benchmarking. So first you have these open domain benchmarks. For instance, for classification, you just have a large set of problems. You can pick them from the web. Some are easy, some are hard. Especially, like these. They are all open domain. You can get them from the web. You can get the data. For instance, the first one means that you have 45,000 items there in the database, and then you just try your own algorithm, and then the other guy's algorithms, and you hope that your algorithm is the best. And then you try so long that it is the best, which is not quite scientific, but that's especially what graduate students do.
Hi, thanks for a very interesting talk. I wanted to ask, what's kind of your philosophy for choosing the problems you decide to work with? So when you started, for example, these deep autoencoders, what led you to pick this problem in particular?
Yeah, that's a good question. That's a hard question, but I think a competent researcher should have a kind of filter in his or her head, which is kind of important and which is not important. And it's quite often, for instance, there's a time when there's a kind of quiet period in a certain field. Like, for instance, when this neural network hype will die, then many of you will go to something else, and there will be a quiet period. And then during those periods, it's time to think what will be important, let's say, after 10 years or so. Because there will be unsolved problems, and even if the companies and the government doesn't just then give money, they remain and they must be solved. And you may become famous if you are solving them before the bandwagon really starts rolling. So there are some important things like not doing what everybody already is doing. Then you're late. I mean, you must be the first, of course. And then doing something that is meaningful, important for the society, in our case, for industry, for engineering. And then something that is challenging mathematically, but you are the best or one of the best people in the world to solve it because you have worked on similar problems. So you may be able to crack something that not every student around you is able to crack. So, okay, maybe I answered you actually.
Thank you, Erkki, for a very nice talk. I have a very technical question. Those unsupervised learning results are really good, as you mentioned. It's very hard, as you say, to get MNIST, for instance, to that level with fully unsupervised system. Still, we, for instance, have been working on semi-supervised learning where you assume that you have some labels. Is it possible to make use of a few labeled samples if they happen to exist? Have you been looking at that problem?
Not here, but I imagine that you just would say that definitely these and these and these items do belong to the same cluster, so something is exactly equal to 1. I guess you could put that kind of constraints even into the learning rule, but we haven't been looking at that exactly. But as you said, of course, this semi-supervision should help, and full supervision should help even further. Yeah.
Okay, thanks Erkki from me as well for the nice nostalgia trip. The question is like, it seems that when reading the internet, you see pretty often actual discussions where people considering a master's degree in data science, they are asking for advice which city and university to do the program in. And it's increasingly, it seems that there's places like Aalto, in addition to Barcelona, Edinburgh, and all the larger cities as well. The question is like, why Aalto then? What would you answer to those students, whether they already have a bachelor or just starting their original studies? Why Helsinki, why Aalto? Why the InfoLab?
Okay, in this field, in a way, InfoLab is Aalto, so that's the same thing. Well, of course, countries and cities have certain attractions that may be very, very important. So for Finland and for Helsinki, I would just use what the tourist office is offering. So nice climate, warm weather, and lots of light, things like that. But then for the actual level of teaching and research, it is fully international. I mean, in some rankings, we were the best place in Europe in machine learning and pattern recognition. Of course, we cannot beat Stanford or MIT, definitely, but not everybody wants to go to America, and not everybody can go because of these immigration problems and so on. So in Europe, we are very, very competitive. But well, there are probably a dozen people in Aalto whose job is to work on this and try to advertise. Finally, it goes by word of mouth. So, for instance, Macadamia has graduated some, I don't know, maybe about 100 people, and they go around, many of them return to their home countries, and they say that, okay, why don't you go there? And the reputation is very, very important.
Thanks for the talk. I will just ask you some general question, and how we know what certainty we have that we are not approaching to a third AI winter, because we already have two. So it's like we are in the right path. Or
okay, well, the two first AI winters, I think they really dealt with the real AI. I mean, with the symbolic AI. For instance, what is called the second AI winter was just because of the Lisp these symbolic list machines lost their market, and expert systems somehow lost steam. That was in the late 80s. And some financing organizations thought that expert systems were great, but not quite as great as they claimed they were. And actually, that was exactly the time when neural networks were able to jump and attack and conquer ground. Now, do you mean by AI this? Is a deep neural network AI to you? That's my question. Well, to me, it is definitely not. But I'm an old timer. So, but there may be a neural network winter certainly. Okay, but now it looks like it's going very, very nicely forward, and it can deliver. I mean, deep neural networks can deliver. They are wonderful. We don't know how they work, but we know they do work. I would like to do it, but I'm too old to answer that problem. I don't know if I answered at all your problem, but it was a different thing with these first two AI winters.
Hi, thanks for the talk. And my question is, I know you would obviously be working on an area which you think is the most promising for the future. Yeah. But in your opinion, observing what people are researching right now, what area would you like more research happen in the near future? Then
I would say that no discipline, like no kind of methodological discipline like mathematics or maybe like even computer science cannot really develop without connections to some other disciplines. So I would say that it would be some cross-disciplinary thing. And like 10 years ago, I said that please go to bioinformatics, because then the human genome project and all those, that was very exciting, and many people went there, and they have done very successful work trying to solve these things of molecular biology with experts, but using computer science algorithms. Now I would almost say that go to humanities. I know this is not very new. I mean, Helsinki University obviously is doing that. They have established chairs in digital humanities, but humanities is one thing where computer science has not yet, or AI has not yet really made a deep impact, but it may be. We have this social media all around, and it has an enormous amount of data that we could have, kind of big data, and that to me that would be exciting. Even language understanding, make a machine understand what you say. That's a challenging problem.
Yes, thank you very much, Erkki. So I guess this is a societal question and about the future of AI and machine learning research. So lately we've seen this kind of I would say an emphasis shift from the kind of university research to company research. So we have Google and Apple, Facebook. They are very central in the kind of deep learning community. They have lots of data, and somehow I feel that the universities can't keep up anymore. So how do you see this for the kind of future of the field, and what will change, and as well, how do you see the kind of like Finnish position there, because we don't have large companies that would actually do AI research, or that would have products that would benefit from that one?
Yeah. I agree. So it's really kind of embarrassing to work on some algorithm when you know, or you can guess that already it has been solved in some laboratory that is not allowed to publish. So who knows what Apple, for instance, has. I think in Finland, in this and in all the other things, we should find some kind of niche, like we find some niche products. Well, Nokia was an exception, but something that where the competition is not so extremely hard. So if you look at what Google, for instance, is doing, and then you decide, okay, that is their biggest research field. Let's jump there. Okay, if you want to join Google, that may be a clever move. But if you want to do original research, then it's a very bad move, because there are so many people there already. This is kind of the bandwagon question. So one should try to find these niche things that these big companies don't do yet. They are saying that they are very free in the research laboratories, but I still think that they have some constraints on what they can really do. But in a university academy, you are totally free to do whatever you think will be useful. And I mean, I always try to find problems for which I am the first one. So I'm very strong one of this NIH, not invented here people. That's why I hate backpropagation, because I did not invent it. I don't want to do any research on it. But I want to do research on principal PCA, neural PCA, and this even some aspects of non-negative matrix factorization, because in some things we were the first. You should always be the first. But what is then? If I only could now give a list of problems that will be extremely important in 15 years, and all of you would be famous for solving those, I would do it, but I don't know that list. I don't know. Actually, if I had, I would keep it to myself. Okay.
And we still have one more question. I didn't see her wave, so she gets
Right.
to give her question.
Sorry, a couple of questions from me. The first one, what is your favorite kind of data? Is it time series or probably something else?
Okay. Yeah, well, I'm really a theoretician.
Mm-hmm.
So I really see data only as a way to do benchmarking on my algorithm. So basically any real world data will do. I hate synthetic data, because if you use synthetic, let's produce some mixture of Gaussians and then try our algorithm. That's not. You have to have real data that is taken from some real environment. But of course, it can be public domain that you just get from the internet. But we've been doing this. We've been using all kinds of data: pictures, videos, emails, documents, speech. But basically, all the research I've ever done is with this kind of input side, the sensory side. So I've never worked with robotics or that. So it must be rich, natural data, a bit noisy, and there must be a lot of it. And then these algorithms start to show their nails and teeth.
And the second question is, you tested the presented algorithm on different kind of data sets, and there are also other data sets with quite high accuracy, with 0.9 and higher. And what kind of those data sets? Could you just briefly explain?
I wonder if I understood. So you talk about this.
Yes.
This.
Yes.
So.
And there are also Brunner dataset, GZ. Just could you briefly explain what are the datasets?
Yeah. Okay. I don't know if we really looked at the data at all. Just take the data and throw it in. So of course, because this is a clustering algorithm, then the more clustered, in a way, the data is. I mean, if we're able to look at the data cloud, then you would see really these isolated clouds and then kind of empty space between. For that kind of problems, of course, any clustering method works very nicely. But if it's kind of uniformly distributed on a square, then the difference between supervised and unsupervised is horribly large, because for unsupervised you can just say, okay, that is class 1, class 1, class 1. So-called clusteredness of the data is very important. Actually, with this algorithm, we can also take a look at that. All data sets are different. You should use some visualization tools, for instance, if you want to kind of try to get a hand on your data, what it's like. And in any practical problem, of course, I mean, then 90% of the work is just massaging your data. It's a totally different problem. Then this algorithm is just a tiny part of the process. And selling the results to the customer, that's the hard part.
Thank you.
Thank you very much, Erkki. Let's give a round of applause.